Hola, muy buen día tengan todos ustedes. Muchas gracias por acompañarnos a un evento más de GTS Parametry Experts. Mi nombre es Víctor Zacarías y soy el director de GTS en México. A nombre de todo el equipo de GTS Querétaro, Coahuila y Sonora, les damos la más cordial bienvenida. Tenemos el gusto el día de hoy de recibir al doctor Stephen Feldbauer de Abbott Furnace y nos va a hablar el día de hoy sobre el control de proceso en procesos de Brazing, específicamente sobre temperatura y sobre atmósfera, que es lo que nos han pedido muchos de ustedes. Antes de iniciar, queremos comentarles que tendremos una sesión de preguntas y respuestas, por lo que les pedimos que nos hagan llegar sus dudas al final de la presentación o durante la presentación a través del chat que se encuentra aquí abajito o a través del panel de Zoom que se encuentra aquí abajo. Entonces voy a cambiar a inglés, espero que les puedan seguir. Si tienen alguna duda, por favor, coméntenlo a través del chat y lo traducimos. Hi, Steve, thank you very much for joining us. How are you doing today?
Hi, Victor. Thank you very much. I really appreciate you having me on your webcast. Thank you.
Oh, it's a pleasure. So today we're going to talk about racing, which is kind of your specialty. Kinda.
It's near and dear to my heart.
There you go. So tell us a little bit about yourself, please.
Okay. My name is Steve Feldbauer. I did my doctoral work at Carnegie Mellon in process metallurgy, and I am the Director of Research and Development for Abbott Furnace Company. And I'm also a senior adjunct professor at Penn State. And so I do a lot of work in brazing and in the process. So.
Correct. You also participate in committees with the AWS, correct?
Yes, actually, I'm very active on the C3 committee for where we write the standards. We do the brazing handbook, and then I'm also the chairman. I've been the chairman for the past 10 years for the International Brazing and Soldering Conference. And that will be held in October of next year. So I invite everyone to submit papers and look forward to attending. And that'll be in Denver. And then I'm also co-chair of the AG CQI 29 brazing standard for the automotive industry.
Excellent. That's something that we really, really needed.
Yeah, hopefully that'll come out within the next 12 to 18 months. That's kind of our goal.
Okay, perfect. That's good to know. Great. Well, thanks again for joining us. It's a pleasure, Steve. So we're going to talk about specifically, obviously, furnace brazing. So the first thing that we need to talk about is the segments of continuous furnace brazing, right?
Yes. So if we start off, what I have here is a schematic of a typical furnace, and you have the load section, and basically you can see that there's a belt that travels through the furnace and it pulls the components through the furnace. So you load here at the front and it pulls it into an initial section. These two boxes, you could either have a two-box design or a single box that is heated. But the front portion of that box, whether it's a single box or two boxes, that's where you're going to remove any binder from any paste. That's where you're going to start to preheat the product up. And then finally, you want to go into a higher temperature area, depending on the metals that you're brazing. And that's going to, in this location, you reduce the oxides and actually melt the filler metal and form the bond and the alloy. And then after leaving the high heat section, you enter into the cooling section. And here, the goal is to bring the product down to room temperature without oxidizing it and causing discoloration. Correct. And bring it out to a temperature that you can handle.
Yeah. Oxidation, it's always the problem. Oxidation and discoloration is going to be always the issue when it's the most that I heard every time I talk with the brazing people. So that's kind
exactly.
of like,
and what we're going to do as we go into the presentation a little bit later, we're going to actually talk about how to do some troubleshooting. Perfect. And we're going to talk about that discoloration and where it comes from and how to evaluate it.
Right. So from GTS point of view, because that's what we do, the most important thing for us is temperature and atmosphere. So probably we need to talk about temperature, and temperature profiling is kind of a must.
Exactly. You know, a temperature profile is a graphical illustration of the furnace's performance. Okay, and you can break a furnace performance into three things: it's time, temperature, and atmosphere.
Correct.
And that time goes into both. It goes into the atmosphere as well as the temperature. So the only way that you know whether your product has seen the appropriate temperature for the appropriate amount of time is to do this temperature profile.
Correct. Okay, correct. There you go.
Yeah, and so what we see here, we have plotted temperature versus time on the bottom axis, and all this is you place a thermocouple in the a part or in a fixture, and you measure the temperature as a function of time going through the furnace. Now, one thing you need to be careful of when you do these, one mistake that people often make is that they plot temperature versus distance. And depending on the speed that you're traveling through, you could end up with graphs that look very similar, but the actual time that you are at temperature is significantly different. Right. So you always plot temperature versus time. And this is a single box. You can see there are 3 zones of control. And so we can, even though the temperature of the first zone is set at 1650 degrees Fahrenheit, which is approximately 900 degrees C, you notice that we're about 200 degrees Fahrenheit low, because you need a thermal head to drive that heat into the product. So that's why it's so important to do a thermal profile, because although the zone temperatures of your furnace may be set much higher, the actual temperature that the part sees as it travels through is going to be different. It may eventually reach the high temperature. For instance, you notice here we peak out at about 1850 degrees, right where our zone 3 is. But prior to that, as we're heating up, we aren't even close to the actual zone temperatures.
Right. Most of our customers ask us, well, why am I having troubles with brazing since my set point is really, really high, so I should get that temperature. Well, that's what the thermocouple of your furnace says, but that's not the whole furnace.
That's correct. Just because the thermocouple of the furnace says you are very high temperature, that doesn't mean you gave it enough time to get there.
Correct. Right.
So that's why that profile is so important.
Right. And well, from our metrology point of view, it's either bad being at low temperature, and at high temperature is also bad, especially for brazing.
Oh, absolutely.
Both are bad.
Yes, absolutely. And we'll actually talk about some of the defects associated with that, because if we go too hot, you can ruin your part.
Right. And if you go too low, you're not melting anything. So
exactly. Yeah.
Yep. Perfect. So the next question is, why should we run a profile, or when?
Okay. Well, there are 2 reasons that you run a profile. The first is to establish a baseline. And so you should always run a profile when you're making good parts, because that's going to tell you, you already know you're making good parts, you have a healthy process, so you should establish what that profile looks like that achieves a good part.
Right.
Then, in the future, if you have a problem, you can run another temperature profile and you can compare them and use those to troubleshoot. And you can say, well, in my baseline, in my good condition, in zone 3, I hit temperature X.
Right.
But in today, I'm not hitting that temperature. Maybe I have some elements out, or maybe something has happened with the insulation. And to your point, so I may not hit the temperature that I need to melt the filler metal and to braze.
Correct. Yeah, we have always insisted that this is a tool, and it could be a proactive tool. Because, well, if you know this information from the very beginning, you know that what your problem is, or it's going to be.
Yes. Yeah. And actually, you know, what we do is we really encourage you to run this at least every 6 months. Okay. Because you would rather plan a downtime as opposed to be forced to go down, and that in a time that may not be good for your production. So if you are proactive, you can stay ahead of the repairs and things that may be needed, and you can then plan things.
Perfect, totally agree. So, okay, let's do a survey. Well, sorry, let's do a profile. What do we need? What do we need?
Okay, so really you need 3 things, okay? You need a method to record the data, okay?
Right.
And that can be, there are different things. We'll talk about that in more detail, but you know, it could be a computer, it could be a data logger, you know, you just need some mechanism to gather that information. Then you need profile thermocouples. And I say here profile thermocouples of proper length, because depending on the technology that you're using, they may be very short, or they could be the whole length of your furnace.
Yeah.
And so you really need to have the right thermocouple for the technique you're going to use. And then finally, you want a thermocouple fixture. And this is something that a lot of people, they make the mistake. They don't use a thermocouple fixture. They say, well, I want the profile of my part. Okay, so I'm gonna use my part. Well, that's great, but you know, one time I was doing a class, and I said, please don't use a part, because here's our goal as producers. 5 years from now, hopefully, we're making bigger and better and more complex parts where we're making more money, right? Well, if you did everything based on a part, that means you have to save that part, or you can't compare the first profile to the second one.
Apples to apples.
Exactly. And what was interesting is I said, and you know, as people advance in their careers, you say, I'm going to save those parts. And they put those parts in the and all of a sudden you get a new maintenance manager who's going to do a good job, and he cleans up and he throws away all the old junk, including those old parts that we don't make anymore. And now all of the thermal profiles that you have done are no longer any good, because you can't reproduce them and you can't compare them. So you're starting over. And that way, if it gets thrown away or lost, you can build it again.
Right. That's a great piece of advice, by the way. I think, just to summarize this, we at GTS highly recommend to document the procedure to run your profile. So every time you do it the same way, so you can compare the baseline to the following profiles. Okay.
Absolutely.
And one thing that I need to add, because we are metrologists, that the recording device needs to be calibrated, and the thermocouples need to be calibrated. And everybody's going to ask, Vic, but why do you always ask me to calibrate everything I have in my plan? Well, because you gotta know if it's reading correctly. So, well, sorry, that's my job, to always be a pain in the ass and remind you that everything needs to be calibrated. If you measure, it needs to be calibrated. Sorry.
Exactly. In fact, everything, what a lot of people don't realize is when you go in to do a calibration, that is traceable all the way back to your national standards. So like in America, it's NIST. And that is part of international treaties, so that when you say that you are at 800 degrees C in Mexico, same exact temperature as it is in China, that's the same exact temperature. 800 degrees is 800 degrees in America. It's and you do that calibration so that your process can be compared to any other process anywhere on the planet. And that calibration's bigger than what they think. You're really not just going in saying, oh yeah, you know, it looks good to us. Right. No, you're comparing that to an international treaty.
Right, right, right. Thank you very much for that. Can you give us an example of a fixture?
Yeah, actually, this is the one that we tend to use a lot.
Okay.
Basically, what it is, it's approximately 1.5, about 2 centimeters high, and it's about 4 centimeters long. And so you can see that this side of the box is open, and you can stick a thermocouple in here, and there are walls. But my point here is, whatever you use as a fixture, make a drawing of it, make it something that you can manufacture so that it's reproducible. And if it gets lost or it gets thrown away, you can build another one.
Correct. Correct. So now you have your fixture. Now what?
Well, what this does is, you can see here, you have your recording device. In this case, it's a computer. And then you have your thermocouple. And what you do is you place that thermocouple in. Be sure that you're not up against the wall. You want to measure the inside, because so often whether it's a fuel rail or it's some type of a container, they're hollow. Okay, they're empty on the inside. So don't put that up here, so it acts similar to a hollow device or a part. And then we put a little bit of insulation, just a little bit of fiber in the back, just so that the atmosphere, you don't get a chilling effect. And you can see here, we then attach the thermocouples to the belt. And in this case, Victor, you're using planar method according to CQI 9, right?
Correct.
And you can see that we have the parts going in, and we have the fixtures, and we have the thermocouples into the fixtures, and the thermocouples are coming out to a recording device. And that can be a computer, it could be a data logger, or whatever.
Correct. Correct. So you mentioned something very important, that the length of the thermocouples, it will depend on the equipment you use, right? Yes. So because the most common, or I will say cheap, data loggers are external data loggers. So you have the data logger outside the furnace, and you start feeding the thermocouples while the belt is running. But we also have those nice pieces of equipment that are wireless. They are not wireless, but but it's a really nice tool.
Mm-hmm. Yeah, you know, if we look at the types of equipment, you know, you really can break it into 2 different schools, okay, or 2 different technologies.
Right.
One is a data logger, and the other would be thermocouples that go to an external device.
Right.
And you know, and there are advantages and disadvantages to each.
Correct.
For instance, the data logger, a common one is the Phoenix system. Okay, and you can see here, there's a photo of the Phoenix system, and that little data logger actually, the big advantages here is that it takes up maybe 2 to 3 meters of space on the belt.
Right.
Okay, and you can load ahead of it and behind it, so it makes it very convenient to run a profile. This is very very widely used in the brazing industry.
Correct.
Now, when you get into other industries like the heat treating industry and sintering, that kind of stuff, because of the length of time that they're going to sit, it's really nice. But they are, you know, there is a cost associated with them. So if you want something that is very, very economical, much less cost, that's when people will go to thermocouples that come out to an external recording device like a computer, but the thermocouples are very, very long, and you are not able to load parts and have production while you're doing the profile. So you would load around the thermocouples, make sure that you load the same way each time, but you are not able to, you will stop your production when you're doing this technique.
Correct,
So,
correct.
Yeah, and it's interesting. One of the things that I ask people to do is look at the cost of lost production.
Right.
Just to give you an idea, a typical brazing furnace produces between $5,000 to $10,000 per hour. So if I lose 2 hours of production, I'm going to easily lose $10,000 to $20,000.
Correct.
If I'm going to do 3 profiles,
Correct.
my Phoenix system's free.
Already paid.
Yes.
Right. That's a good calculation. It's always good to see the numbers, actually.
Mm-hmm.
Great. So in your experience using this kind of data loggers, what do you think are the benefits?
Well, like I say, the biggest benefit is that you can run it more often and not be as disruptive. So like I say, you need that 2 to 3 meters of space on the belt, and then you can continue to make production. And so people are going to be more profile because it's not as disruptive to production. So that means that when you say, please run a profile every 6 months, they say, yeah, it's not a big deal. I can do that. But if you tell them you have to empty your system and you're going to be down for all these hours, well, because because what you have to remember is you not only lose the production while you're doing the profile, but you also have to reload the furnace. So you lose more than just one pass through the furnace. So, and if it takes you an hour to go through the furnace, you're going to lose 2 hours of production. Right.
Excellent. So, okay, we have our thermocouples, we have our data logger. What's next?
Okay. Well, actually, and this is one of the big advantages. Like I said, to the Phoenix system, there's software that goes with this, that when you bring this out and you bring it into your computer, you download the information, you can put do that. They actually produce a system that has telemetry, so it'll actually transmit as well. So you can do both. You can actually get information in real time. And then but to answer your question, once we have the thermocouples, we have the fixtures, there's then an enclosure. Okay, and that's what we see here in the picture. The data loggers inside of this to protect.
Right.
In fact, here you can actually see how we would fit a data logger into a box, and then you see it's very hot, and the thermocouples come out of the box, but the data logger is inside. And so, like I say, you have the option to do downloaded, or you could actually do wireless and telemetry with the Phoenix system.
So okay, we have data logger. What's next?
Okay, well, once you get the data logger through, then what you want to do is you need to look at that profile. And this is, and you can see, you're able to go in, you can put different event markers in, and you can see that thermal profile as it traveled through the system. So, and here, what you can see is in the case of a connected to the computer, you would have using data on the computer. You would then come in and you would record. Okay, but this type of a system where you use the long thermocouples and the computer, it's able to profile up to extended time, because what happens, you start to have difficulty with the signal that's coming back when you get to event marking. You can actually use the thermocouple that's traveling through and mark the thermocouple, so you have a physical indicator of position. Where the Phoenix system, you have to do it based on belt speed and time. But this, and the other big advantage to this equipment is it's
the problem with the limitation with a telemetric system is that temperature is going to be your problem all the time, because there's a limited amount of time where the box can resist temperature. So for example, I think the longest time that you can stay inside the furnace is about 4 hours for some systems. It really depends on the size of the box, of the thermal box, but that is going to be something that you need to think about when selecting the right equipment for you.
Yes, I know that there has been some experimentation and development in trying to extend that time. And I've been part of doing some profiles that are in sintering applications where they're sitting at temperature for in excess of 30 minutes. But that has yet to come to market.
Right. That's something that we need to think about. So, well, there's always the option, like you mentioned, of having a very long thermocouples and having your external data logger to record temperatures.
Right.
Correct. So, okay. So what do we have after we run our profile?
Well, this is a typical profile from a thermocouple and computer system. And you can see here, this was a 2-box design. And you can see between boxes, and you can see the location of each one of the thermocouples for the zones, where it exits the preheat section, enters the second box, leaves the high heat, so it's similar. They both will produce, both technologies produce a profile that will meet CQ9.
Correct. So, so what would be at the end the overall procedure for the whole?
Yep, and like you had touched on before, the first thing we need to do is calibrate all of the controllers. Use calibrated thermocouples. You want everything to be traceable. It is very important for you to always use the same atmosphere flow rates and the same atmosphere composition, because the atmosphere plays a large role in the way that the energy is moved throughout the furnace. So for instance, hydrogen will absorb 14 times as much energy as nitrogen. So in cooling, if you had more hydrogen, it will cool, the atmosphere will cool your product faster. However, if you are in heating, once you've heated that atmosphere, when it comes forward into the hot box, it carries heat towards the front door even more, the hydrogen will, as compared to nitrogen. So you always want to have the same atmosphere flows and same atmosphere composition. Likewise, the same furnace loading. You want to compare an apple to an apple.
Great advice. Thank you. So what's next? You have the procedure. I think one of the main things is to run your profile every time the same way. So
Exactly.
when to do the profile?
Well, you know, you really should do the profile. We really recommend that when you first get your furnace and you first start up your process, or if you've been down a while and you turn your process on and you're making a good part, profile. Do a profile, mark that as success. This is good. This is a good condition. Then every 6 months, you should do another profile. And that way you can be proactive in trying to head off any problems. And you can compare that to your baseline. And as things change, then you can plan your maintenance so that you're always making good product. And then likewise, if something does happen, if you do have a failure or something, you have an issue, then run the profile again to do the troubleshooting.
Correct. That's really good piece of advice. So this is for temperature. I think it's time to move to atmosphere. That's the other variable that always is going to be a pain for us.
Yes. And you know, and they go hand in hand because atmosphere, you have reactions that occur in the furnace. Okay. So remember what we said, we loaded the parts at the front of the furnace. And then as we went through, we heated the product up and then we reduced the oxides. Well, what's happening is we put our hydrogen and nitrogen in the back and they're flowing towards the front. That hydrogen will actually react with the oxides on the surface and form water. So what you see is, you notice how the amount of water goes up as you go towards the front of the furnace, and the amount of hydrogen goes down slightly. And that reaction is a function of temperature.
Correct.
So they go hand in hand. So that's why we recommend you do both.
Right.
You have to regularly do a temperature profile. It's something that's easy. It's not as invasive. But now you want to also look at atmosphere, because the atmosphere is the workhorse of your furnace. It's what reduces the oxides. It helps transfer heat. It helps flush away any kind of oils that vaporize off, any of that. That does the work.
Correct.
Okay.
Perfect. So, well, we need to talk about why we use atmosphere.
Yes, and that's why it's the workhorse, but it does two primary things. It prevents oxidation, and it reduces the oxides that are on the surface.
Correct.
Because in brazing, the first step in brazing is you heat up the product and then you reduce the oxides so that the filler metal can flow over the surface and form the alloy and form the bond. If you allow that oxide layer in there, it acts as a barrier between the filler metal and the base metal, and you won't get bonding. So those are the two principal functions of the atmosphere: keep air out of the furnace, and reduce the oxides on the surface of the metals.
Right. So the purpose of this webinar is not to talk about the science behind brazing, but just having in mind that the surface condition is just the basic to have a good brazing. That's all you need. But if you want to talk, well, maybe later we can talk about all the phenomena that goes into brazing, the wetting, the diffusion phenomena, that all stuff, that shitty stuff that we need to know. Yeah, but, because we need to understand what is going on, what is happening in order to solve the problem. But probably for the next webinar, we can talk about that.
Yep. So.
Perfect. So, well, okay, we know atmosphere is important. So what do we do with it? How do we know it's right?
Okay, well, that's where the atmosphere analysis or the atmosphere profile comes in. Okay, and so what we're going to do is the atmosphere analysis is a little bit different than the temperature profile. Here, what we're going to do is take a stainless steel or inox tube, and we're going to insert that from the front of the furnace and slowly move it through the furnace and gather a sample at each location as we travel through the furnace so that we can look at what the atmosphere is in each location.
In every section.
But because it takes time for that atmosphere to get through that tube,
right,
we have to allow it to sit there for a while. So it's not going to travel through fast like the thermocouples do,
right,
or the Phoenix system. It's going, you insert and you let it stabilize, and then you move it again and allow it to stabilize, and you gather that information. But it's very important because this is what gives you the information to tell you if your process is correct, okay, if the atmosphere is correct in each location, in conjunction with the temperature profile.
Correct. Correct. So, well, I think we are all familiar with the temperature profile, but you always bring a good concept that it's atmosphere profile. So can we talk about that a little bit?
Yep. So it just like the temperature profile, it's a graphical illustration of the atmosphere composition inside the furnace. So as you can see here, this red line, okay, is the hydrogen level, okay, as we would go through the furnace. The blue line is the oxygen level as we travel through the furnace. And then this green line is the dew point as we travel through the furnace. And like I said, we did that by you insert that tube and then you allow it to stabilize and you record the information. And then you advance it and allow it to stabilize and record the information again until you're able to travel pass all the way through the furnace.
Correct. So what do we need to do that test?
Okay. Well, the typical equipment is the most common is actually the dew pointer.
Right.
Okay.
Right.
But also you will see that just like in the previous slide, people will look at the hydrogen level or the oxygen level. Okay. And so you'll need a hydrogen analyzer, an oxygen analyzer, a dew pointer, a copper tube, and a stainless tube or inox tube. That inox tube, that stainless tube, is what goes into the furnace. And because it's very stiff, we connect the copper tube to it so that we can have some flexibility to connect to the measurement devices. The dew pointer, for instance, is going to sit external to your furnace.
Right.
So you need to be able to connect up to it and give yourself some flexibility. Right.
So basically, if I understood well, you have the copper tubing outside the furnace in order to move a little bit, right? And the stiff part is going to be inside the furnace. That's going to be the stainless tube.
Correct.
Right. Correct. Usually, these kind of analyzers, they are commercial, right? The manufacturers. It's usually an infrared sensor or a humid, relative humid sensor, right?
Right. They'll typically, yes. There are a number of different manufacturers. They'll use thermal conductivity, or they'll or infrared, that kind of thing. It just depends on the technology. But there are a number of different commercial pieces of equipment available. And if I had to list them in the order of importance, actually these are upside down. I would say dew point, oxygen, and hydrogen would be last.
Correct. Correct. Every time we talk about brazing, we are going to talk about dew point. That's something that we need to discuss. Correct. So that piece of equipment that you have there, is that something that you use for validating your furnaces and Abbott furnaces?
Yes, actually, what I'm just showing this as an example, of a sample cart. Okay. There are two ways to put these systems into operation. You could mount the different devices onto the furnace and have a dedicated sampling system. Okay, but that equipment that you've now purchased, that dew pointer, is only for that furnace. Another approach is to do a cart. So what this is, it's a cart where you put the different devices on that cart, and then you can move that cart from one furnace to another furnace. And it now has more, it's more flexible, it's more functional. You can use it throughout your facility, not just on one furnace. And so you know, and these sample carts, they can be equipped to do atmosphere balance. So, you know, to use atmosphere composition, as well as you can optimize the cost of your atmosphere, because, for instance, hydrogen is twice the cost of nitrogen. So by balancing your furnace and only having that expensive hydrogen where it will do its work, okay, you then optimize it, and you're not flowing it out the back of a furnace and wasting it.
Right, because every time I go to a brazing plant and they have a problem, usually, hey, increase the amount of hydrogen. Of course, make it more expensive. That's the solution everywhere, you know? Like, yeah, put more hydrogen there. Like, sure, why not?
Yeah, but this allows you to optimize and hopefully save some money.
Right. So can you tell us a little bit more about your cart? Yes,
you know, just as an example here, you can see that, you know, this has some digital displays, so you can see the readout from the various devices: dew point, oxygen, hydrogen. This is the oxygen analyzer. Like I said, there are different manufacturers of these. The dew point analyzer is this portion, this white portion with the tube back here, and the cell is actually up inside. And then this canister, or this gray device here, that's the hydrogen analyzer. And so, and this cart is actually equipped with the I/O device, so that you can do the data logging as well. So you can set your laptop here and, you know, your computer, and you can connect up and you can run the thermocouples through on this device. So you can do both. You can do the atmosphere profile as well as the temperature profile with this.
Which will be ideal, right?
Yes.
Correct. Okay, we have the equipment. Now what's the baseline in case of atmosphere?
Yeah, the key here is, just like in the thermal profile, we want to establish a baseline condition. So again, when everything is working, do an atmosphere profile, so you know what that atmosphere composition should be throughout your system. Check the dew point and oxygen at all of the incoming gas as well. That's one of the first things that when you go to do an atmosphere profile, always start at your incoming gases to make sure that you're not feeding, you know, garbage in and garbage out, right?
Right.
And I've seen this happen, especially if you're using tube trailers. They bring in a contaminated trailer and it ruins the whole furnace. Well, you know, ruins the atmosphere in the furnace.
Right.
You know, it'll say that you have a high dew point in the furnace if you look in the furnace, but it's not because there's a problem in the furnace. You're bringing in contaminant. So always check your incoming gases. Then determine the profile, like we had mentioned, and then check the dew point and O2 content in all parts of the furnace. So oftentimes you can do that profile, but if you wanted to do quick checks, many furnaces have the ability just to do a sample of the atmosphere in the coolers.
Right.
So you could check in the cooling section, or maybe some of them have the ability in the transition between two boxes of heat. But you can do quick checks just to validate, but that does not replace the atmosphere profile that goes all the way through the furnace.
Agree. So when we discuss about furnace brazing, you always bring a really nice example of the before and after. Can you show us that? Yeah, please.
Yeah,
Thank you.
this is, well, if you notice, you know, atmosphere, when you introduce it into your furnace, you should have, you put it in the cooling section. And remember, we said we want that hydrogen to go forward because it's expensive. We want it to go forward and do the work in the hot box. And we only want about 10 to 20% of that to go back towards the back of the furnace. And we want that to mostly be nitrogen in the back, because all it's doing is allowing the atmosphere, it's just keeping air out and allowing the product to cool. If you look at this hydrogen line, we have the same amount of hydrogen all the way through the furnace. So what's that tell you? I'm wasting a lot of gas going out the back of the furnace. I'm wasting hydrogen, you know, and you see, you know, our oxygen level is fine. Our dew point level, you know, we can see that it's going up as we go forward.
Right.
You're making good parts in this condition.
Absolutely.
You're just wasting money.
Right.
Okay. Now, if we go back in and we balance that furnace, now look at this. Look at how this is where we're introducing that hydrogen. Okay. And notice how we introduce it and it goes forward. And we have that high, we have that 8-9% going all the way forward. But notice going towards the back, it drops down to next to nothing. Now we're not putting hydrogen up the stack and wasting it. We're putting it where it needs to be.
Right.
Yep. And so you can see we still have a controllable oxygen level. You know, you see that this oxygen level jumps a little bit in the back, but it's staying, you know, below 10 parts per million. It's not an issue. So everything's in control, but you've optimized your costs.
Correct. So, well, that's a really good point, cost, but I think everybody's waiting to that we talk about problems.
Yes. And so when you know, the atmosphere is directly related to a lot of the issues in brazing.
Right.
Okay. And so that's why the atmosphere profile and atmosphere troubleshooting are so important. Okay. And here are some examples, and we'll go through these in detail, but we'll talk about frosted parts, oxidation, belt oxidation, flashing, inadequate braze, and nitriding.
Correct. Nitriding. Okay. Okay.
Yep.
So let's talk about frosted, which is pretty much common.
So if you look at the picture, okay, here you can see that notice how the part on the left looks a little dull, or kind of almost like it's a little, you know, it's not as shiny, it's not as bright as the one on the right. That's what we're referring to. And what has happened is there's oxygen getting to that part while it's heating up. And so it's forming an oxide on that surface. So now the surface isn't as smooth. And when it goes into the high heat where you have that hydrogen doing its work, it reduces that oxide, but it creates little cavities or little bumps wherever the oxygen was. And now it reflects light different than something that did not oxidize. So that's why you get this dull appearance, okay? So what's happened is you had oxidation in the preheat, okay? Or you could just have too high of an oxide level, or an air leak in the front end, or you could have a crack in the muffle, or a leak in that front air. Or it could be as simple as you have a downdraft coming down your stack. You know, if the wind blows across the stack and it goes down the stack and into the furnace, and it pushes air in the front of the furnace and oxidizes that part.
Yeah.
So, yes.
Yeah, well, when we talk about this particular issue in the front of the furnace, sometimes the problem is as simple as there is an entrance, or there is a door to outside the plant just in front of the furnace, and all the air is entering directly to the furnace, to that gap, through that gap.
Yes, in fact, we get the most number of calls
Yeah.
in the spring and in the fall.
Right.
And the reason is in the spring, everyone has had the doors closed and the windows closed through the winter, and now it starts to get nice and they want fresh air. So they open the doors and they open the windows, and all of that air comes in and it changes the pressure and the balance in the building.
Right.
So that affects the furnace. And another one are fans.
Uh-huh.
So you get into the summer and it starts to get warm. So they put a fan and they direct the fan right at the front of the furnace.
Right.
And it blows the air in and it causes this. So always be careful of doors and fans. And then in the fall, it's just the opposite.
Right.
They turn off the fan. They close the doors because it's getting cold.
Right. Right. All over the time. Okay. So
Yep.
frosted, one thing. Another thing that I always hear is discoloration.
Yep.
Or, well, it's actually oxidation, right?
Right. Surface oxidation, you can see here, you see different colors, right? And it occurs, typically it'll always occur, if you see discoloration like this, it happened in the cooling zone. And the reason is, if I oxidized in the front of the furnace, we would have a clean part, but it would be frosted.
Mm-hmm.
Okay, if I oxidized in the high heat section, it's going to look black, okay, because the temperature is very high and everything's very reactive.
I see.
If I get, the only time I'm going to get a color is in the cooling section.
Mm.
So it definitely occurs in the cooling section, but that means that it could happen from two ways. It could be either air, or it could be water, because those coolers are water jacketed. And so if you have a cooler that's failing, you could cause oxidation from the water leaking in, okay? It's a surface effect, and it will vary with part weight and temperature. So here's where your temperature profile will go hand in hand with troubleshooting, because it will occur, certain colors will happen at certain temperatures. And so we can use that.
Right. So basically, there are basically three things that could be discoloring this thing. It could be air, it could be water, but it could be also carbon dioxide, right?
Right. Well, it really depends on what you're doing, how you're processing your part. If you're using exo, okay, but you have that extra element there of the CO, where if you're doing hydrogen, nitrogen, it would only be air or water,
right? Because
you aren't seeing the CO component. Yes.
Right.
So if you have a generator issue, that could also cause discoloration.
Again, that's the importance of measuring the atmosphere. You will know exactly what is going on inside and where the problem is.
Mm-hmm.
Correct.
And also, to your point, measuring the incoming atmosphere.
Uh-huh.
Because that'll tell you if it's your problem is at your generator or it's in the furnace.
Right. So every time we do the live events, the Abbott Symposium, you bring a really nice chart with the colors, with all the rainbow colors that we can get with Brazing troubleshooting. So yep. I think that's a very nice guideline to find out what's going on or what the problem is.
Yeah, I mean, here it is. This is the color, what we call our color chart. Okay, and what this is, steel will oxidize to form different colors at different temperatures. Regardless of it being air or water, it'll form these colors. And so at about 200 degrees C, you have a faint straw, and you can see this range. But as we go up in temperature, okay, you notice that the colors become more brilliant, right? They're, if you're going to ruin a part, let's make it pretty, right? So they become peacock and blue, okay? Well, and by looking at the color, you can then tell exactly at what temperature it saw the oxide source, the oxygen source. So for instance, if you see a product that has this peacock color, okay, similar to that gear that I showed you before, well, you know that that happened at about 282 degrees C, or about 540 degrees Fahrenheit. So now you can go back to your temperature profile and it'll tell you exactly where that happened in your furnace.
Love it.
So now you know, okay, it's a color, it happened in the cooling section, but where? Now we can say, oh, well, this happened at 282 degrees. My thermal profile tells me that's my third cooler.
Right.
And so now you can try and troubleshoot that cooler.
That's where exactly the problem is.
Exactly. Yep.
Excellent. So this is the best case scenario. I have seen parts like really, really, really bad oxidized. Like yeah. I mean, if they are really heavily oxidized, okay, if they're black or gray, or maybe even you'll see them peeling. Okay, you'll see the oxide flaking off. That means that it happened in the high heat. Because if you recall from the color chart, you notice how it keeps getting darker. Once you go very high in temperature, that oxide becomes very dark gray to black. And that indicates that you have a leak in the high heat area. And it could be a hole in your muffle, or it could be some other cause, okay, or source of getting air in there. What's the most common case?
Well, typically, if you see this kind of an oxidation, it's typically due to an air leak in the muffle. Or if you have a sealed box, it might be that you have one of the covers is leaking.
I see.
Yeah, but it's typically some air is gaining access to the high heat.
Perfect. Yeah. Also, when we talk about these kind of issues, you also discuss about the copper and the stainless steel test, which I think it's very pragmatic. Yeah,
this is, I think it's a test that is not used enough.
I agree.
Because this is a way for you to troubleshoot your own furnace, okay? And it gives you knowledge so that when you do have to call for help, you have information to share, and it really speeds up the solution.
Right.
So the way that this is done is we're going to determine if the oxidation is occurring in the cooling section, okay, whether it's caused by air or water. So we have a color, okay? We know the temperature, okay, but so we, like our example before, it was peacock. We knew it was in the third cooler, right? For our example.
Right.
But is it a water leak or is it an air leak? Okay, do I have a leak at a flange, or did I wear the bottom of the cooler and I have a water leak? Okay, so this will actually help you. So the first thing you want to do is reduce the furnace temperature to 1900 degrees Fahrenheit. That's because you want to be below the melting point of copper. Okay, so you take your highest temperature zones and just lower them below the melting point of the copper. Then what you're going to do is you're going to take a piece of copper. It could be a piece of pipe. It could be a shim that you've bought. It can be anything.
Anything.
Just pure copper. Then you want a piece of steel, just a plain piece of steel. It can be, here again, it can be anything. Nice, just a piece of regular carbon steel, and then a piece of stainless steel or inox. And so what you want to do is you want to take some sandpaper, and you want to clean the surface of those and get them very bright and clean. Then what you're going to do is you're going to remove, remove the hydrogen, and then you're going to run this through. And what's going to happen is when the copper comes out and the steel comes out, you're going to look at it. The steel should be discolored and it should match, for example, in our example, if we were looking at peacock, it should be peacock colored. It just confirms that it happened at that location. Then look at the copper. If the copper is oxidized, you had a water leak.
Right.
Or, excuse me, an air leak.
Right.
Okay. If the copper is nice and clean, you have a water leak. And here's how you remember that. We use copper pipe in our houses for plumbing.
Right, for water.
For water. So we know it's okay to put water into copper. It won't affect it. But if there's air, it will oxidize it. And so this gives you the location and it gives you the source. Is it an air leak or a water leak? So now you're able to troubleshoot that cooler.
Beautiful, beautiful. Very simple test, very straightforward. I like it. So, okay, well, this is really good when talking about problems with parts, but also customers usually come with the problem that the actual belt is discolored. Right.
I mean, the belt is made of stainless steel.
Right.
It contains chromium, so it's very, very reactive with any kind of water or oxygen. And in many times, if you're brazing carbon steel parts, your belt will change colors long before your parts will.
Right.
And so you should always watch the color of the belt. If the belt is dark and the parts are bright, what that means is you're just starting to get some type of oxygen source in your furnace. It could be water, it could be air, it could be a leak somewhere. But if your belt is starting to change colors but your parts aren't, that means that it's a small leak. It gives you the opportunity to catch this before it ruins product.
Right.
Okay.
Right.
If the belt is clean and you have this really adherent, really adherent oxide, typically that's what's happening in the front of the furnace, and it's oxidizing so much that you don't have enough hydrogen in their furnace to clean it. And so if it's very adherent and you can't, and it's typically happening in the front.
Correct. Okay, so we're talking about discoloration, oxidation, flashing. Yes,
flashing. When you look at a brazed part and you see that the filler metal has just run everywhere, right? I've had some people say, but it makes the prettiest gold parts, right? And, yeah, okay, maybe it does.
Yeah.
But what has happened is the atmosphere is so reducing, okay, that it's cleaning the surface so much that the filler metal just runs everywhere.
Spray.
And this can cause a reject, okay? Because your customer will tell you, I don't want that. No. And so the source could be a couple things. You could be too high in temperature. Remember, we talked about being too high isn't good as well. You could actually have too much hydrogen. You could be too reducing, okay? So, or you could just be sitting at your brazing temperature too long, and it's now cleaning things so well that it runs everywhere. So really the solution, I mean, when you tell a production person that they're allowed to increase the speed to get rid of a problem, honestly, I've had them look at me and like, really? Yeah, you're lying, right? I'm never allowed to increase speed, right? But yeah, you can increase speed, reduce the time that you're in that reducing zone, or lower the temperatures, or reduce the amount of hydrogen. But I would do in the order, I would start off by maybe reducing the hydrogen a little bit because that's expensive, and then increase your speed a little bit, and then only adjust your temperatures. Because lowering the temperature is going to save you some money, but nowhere near as much as the atmosphere or the speed. 72% of your cost in your furnace is atmosphere.
That's a great piece of information. Okay. Yeah. It, it's good that you bring this up because usually when problems happen in furnace brazing, we do three things. Increase temperature, increase time, or increase hydrogen. Like, come on, like, no, that's not solving anything. It's making it worse. So thank you very much for bringing that up. Let's talk about nitriding because that's kind of particular.
Oh, okay. So nitriding, what happens, some grades of stainless steel that have higher chromium levels will actually react with nitrogen in your furnace, right, to form a chromium nitride or a carbide, a chromium carbonitride. And so what's happening is between 400C and 900C, the nitrogen will go down and it'll hook on to the chromium and form a chromium nitride. Now, why is this a big deal? Well, the problem is if you nitride the surface while you're entering the furnace, it acts just like an oxide contamination and the filler metal won't flow. Okay? But if it doesn't happen in the front, because you're going from 400 to 900, if it could happen in the back. And you say, well, I've already brazed, what's the problem? Well, the problem is if you form the nitride as you're cooling, what it does, the way that, that stainless steel or inox works is that the chromium will, as it comes out of the furnace, will oxidize, and it forms a very tenacious sealed layer of chromium oxide, and it prevents oxygen from getting to the base metal underneath, and it protects it. And the wonderful thing about inox is that the oxide is bright and shiny, right?
Already, yeah.
People like it. Well, the problem is if you have nitrogen in there and you do what's called sensitization, instead of all of the chromium being connected with oxygen, you could have a nitrogen atom in there, and it doesn't form that nice sealed layer. And now it can allow air to go through that layer and get to the base metal. The scary thing is oftentimes people will not see this, and they'll ship because it's not visible to the eye, and they ship it to the customer, and only after it is gone through, put into service, and it starts to pit. And you'll see that the part will start to corrode, and then they'll call you up. And in the case of the automotive industry, that's the mortal sin, right? You've had a in-vehicle failure.
A recall.
And yeah, and now they come in and the world just flies apart, right? But so nitriding should always be considered. What you want to do is you want to look at the amount of chromium that's in your product, and it's a metallurgical thing. Just ask if you're not sure, and work with the furnace company and the metallurgist.
Okay. Great, great. Okay, I think we have covered all the troubleshooting. And man, we've been talking a lot of so just to close, we're going to give a little time for all the audience to make questions, but let's make some conclusions.
Yep. So basically, if you go away with anything, I want you to go away understanding that you need to establish good baseline conditions, which include a good temperature profile and a good atmosphere profile of your process when you're making good parts. If you then perform routine checks, every 6 months you do your profile, at least once a year you do an atmosphere profile, and once every 6 months you do a temperature profile, that will allow you to hopefully schedule downtime and not be surprised by it. So you have control of your destiny. And then when a problem does occur, do the temperature profile and do the atmosphere checks to isolate the problem, and then use some of the tools that we gave you to try and locate the problem and address it.
Beautiful. Excellent. All right. So let's give a minute to hear the questions from our audience. I'm going to shift to Spanish.
Sure.
Entonces, si tienen alguna pregunta, nos pueden hacerla llegar a través del chat o a través del panel de preguntas y respuestas. We already have some comments, more than questions. We have comments because we have people from many parts of the country. Actually, we have people from the States. We have people from Arizona, Puebla, Baja California. You have been all these places already. So, so there's a lot of aerospace and automotive, which is good. There's one question here from Alejandro Cimental. Actually, I think we have already solved that question. What kind of instrument or device is used to graph atmosphere profile? And I think this question comes because we usually do the temperature profile, but not all the times we do the atmosphere profile.
Yes, usually what is done is you bring the sample out and you measure say the dew point on the dew pointer, and then they record it and they enter it into either manually onto a sheet or into a computer at that point. There are systems where you can go straight into a data logger if you choose, but honestly, most people, for flexibility, just record it because you're going to have time between while it stabilizes from one location to another.
Perfect, thank you. So we have one question from Axel Diaz. Hello, everyone. I have an issue in my plant regarding brazing process, and I don't know what's the root cause. The matter is that the filler metal, copper, gets a silver coloration after the furnace. Silver coloration, copper filler metal. Is
it forming the joint? Is it melting and flowing in, or is it staying as a ball?
Okay.
Because if it's staying as a ball and it's that silver color, you're oxidizing the filler metal as it enters the furnace. And so it's getting so much oxide on it that it won't melt and flow. If it melts and it flows and it forms the joint, what you have is an oxidation occurring in the exit of the furnace.
Interesting. Okay.
Does the part itself look discolored? If the part looks discolored, then use the color chart and use the troubleshooting test.
Axel, we can send you the color chart because I think it's a really nice tool. Very simple to find out where the problem is. So, okay, so we have another question from Jose Luis Armendariz. What happened when the part is bright, but copper filler metal has different colors, silver, purple? I think it's a related question.
Yeah, it typically that is caused at the front of the furnace. You've oxidized that filler metal, and what can happen is the filler metal is not pure, especially if you have paste.
Right.
They add elements to the filler metal to lower the melting point.
Exactly.
And if you oxidize those elements, okay, as you're going in, then the filler metal may not melt. The part could be bright and shiny because it goes into the high heat and it cleans it, but like I say, it could be different colors. Likewise, as you're exiting, if the part is, typically it would discolor the whole part if it's happening in the cooling section. So most likely you've got an oxidation problem in the front of the furnace.
Right. Yeah, these particular issues are happening specifically in the filler metal. So yeah, we have to remember that usually the filler metals are eutectics mixtures. So there's always going to be additional elements that are going to low down the melting point, and that we need to have that in consideration when selecting the right process.
Yeah, in fact, the most common element used to lower the melting point is boron. And if the boron, if you have a high dew point in the front of the furnace, the boron can either oxidize, or if there's water vapor, it'll form boric acid and turn to a vapor. And you lose it.
Yeah. It's funny because we have the kind of the same issue with vacuum brazing, but it's a different mechanism. So boron is always a pain.
Absolutely. It has a low vapor pressure. Yes.
Exactly. Exactly. So boron is going to be always the problem in the filler metals. So Jose Luis, I hope this answers the questions. Also, we have another question from Arjun Rehani. At times we have observed that when we apply copper brazing filler metal on our steel components, there is a carbon deposit observed where the filler metal is applied. What could be the reason?
Okay, when they make a paste, okay, the filler metal, they take powdered copper with some other elements, but they typically mix it with a binder. Mm-hmm. And that binder is a hydrocarbon, okay? So it could be glycerin, it could be different things, methanol, whatever. But what happens if you're heating up very, very fast, if the binder goes above 550 degrees Celsius before it has a chance to actually go through the phase change and boil off, it will actually dissociate and it will fall apart and form soot and hydrogen, and the hydrogen floats away and the soot is left behind. So that's the carbon that you're seeing. So there are two solutions. Well, the one is that you never want to hear is slow down, right? So that you don't, ramp up so fast. The other is to actually increase some of the hydrogen and flow so that you can push some heat towards the front a little bit more, so it heats up a little more gradual. Mm-hmm. And you take advantage of the gases coming forward and you heat up a little more gradual towards the front and by the door, and that'll help with that. But I've seen, usually it's just a single dot that's the issue. I mean, if it's really bad, you can always switch to a preform and get away from the paste altogether. And now you don't have a hydrocarbon in it. It's a solid piece of metal, and now you won't have any carbon.
Interesting. If preform is a solution, or it's something that they can be done, is there going to be affected pricing?
Yes. I mean, preforms are usually, they're typically more expensive because they're actually, they will shape the metal, either a washer or a ring or whatever, to fit the joint.
Right.
However, I've seen people save money with them because they are exactly the right amount of metal every time. When you have people putting paste on, sometimes they put too much. And then you're wasting. So it can go both ways. So if you have a problem, in brazing, they always say if a little is good, a lot is better. No.
No, does not apply here.
Correct.
All right, thank you, Steve. So another question from Axel. This is an interesting question. Does the brazing is affected by varying the load in the furnace? Example, if we braze 1 kilogram per minute and then we braze 500 grams per minute, so half the load. That's interesting.
It will oftentimes, because what's happening is the thermal load will affect the heating rate. Mm-hmm. So you have two ways that you can go. You could, if you've got a light load, it could actually get hot very quickly and you could overheat, and we could have flashing, we could have the sooting of the filler metal paste, that kind of thing. But on the other side, if everything's working great with the light load and then you load it very heavily, what you have to remember is heat goes from the outside in. And if I start with a very small part and I stack them up and I increase the load, now it takes more time to get that heat all the way through, and I'm going to have variation in how it heats and the rate. It'll heat slower with more thermal load. And so now I may not hit my brazing temperature.
Right. Great. Another question from Luis Rodriguez. Hello. the band has scales, I guess is the belt.
Yeah.
Can they be eliminated with oven parameters, or is it necessary to do some physical cleaning? That's always the question.
Well, if the band already has the scaling, if it's already oxidized and scaled, it's not, more than likely it will not clean up. If it's really severe, it's not going to clean up to a clean belt. And the only way to get it with the hydrogen, the only way to do that is if you were to mechanically remove it. But even then, it's going to be very difficult because of that very intricate weave. And so if you have severe oxidation of a belt, unfortunately, you can clean the surface, but you may have to live with it.
Yep. Yeah. That's the bad news. All right. I think that's all the questions we have for today. But we are going to share Steve's email. Are you okay with that, Steve?
Absolutely. Yes, please.
Please go ahead. I've been working with Steve for the last four years, and it's been always a pleasure to talk with him because he makes learning enjoyable. He's a great teacher. So I encourage you to contact him if you have any issues. He knows the stuff. He knows the shit. So
thank you.
So okay, just to finalize this, Steve, I always ask my my host, what is the most important book or books in your life?
Well, I think for brazing, everyone should look at getting the Brazing Handbook. That book has, it covers all the filler metals, it covers all the different processes, and it's continually updated. And you can get it at the American Welding Society's website. It's a really valuable book, okay? And that, I think that in our industry is probably the Bible. It really is. And then for myself, I think Harry Potter is good. Good. It's always good to try to be the wizard. But get the Brazing Handbook first.
Okay. Right. Well, metallurgists and material specialists are always like misunderstood wizards because they don't know what the hell are doing in the plant. Nobody understands what they are doing, but they kind of solve problems in a different way. So
absolutely. Yep.
Right. That's awesome. So Steve, thank you very much for the time. It's been such a pleasure to have you in this session. I hope we can do another one.
Oh, absolutely. And thank you so much for inviting me. It's really been a joy. I've enjoyed it. Thank you.
Excellent. So I'm going to shift to Spanish. Muchas gracias. Estamos muy agradecidos con Steve por este tiempo. De hecho, es probablemente el webinar que más tiempo nos hemos tomado. Por el momento es todo, pero no queremos finalizar sin antes agradecer nuevamente por su confianza en GTS Parametry Experts. Los invitamos a seguir atentos a nuestras redes sociales para el próximo webinar que se va a realizar a principios de noviembre y va a tratar precisamente, ahí vamos a profundizar un poquito más sobre perfiles de temperatura. En este caso hablamos tanto de temperatura como atmósfera. La siguiente webinar vamos a hablar más sobre temperatura. Antes de finalizar esta sesión, les pedimos que se mantengan en línea para contestar una muy breve encuesta sobre su experiencia en este evento. A nombre de todo el equipo de GTS Querétaro, Coahuila y Sonora, les agradecemos su confianza y les deseamos un excelente día. Hasta la próxima. Thank you, Steve.
Thank you. Have a great day, everybody.
Bye.
Bye-bye.